Okay, this is the Virtual Residency Workshop 2022. It's Tuesday, June 28th. This is the mid-afternoon session. This is the Research Networking Overview, and I'm going to turn the show over to Wallace Chase. Take it away, Wallace.
All right, well, thank you, Henry. I hope everybody's had a good day so far in the workshop, and coming in as the last presentation of the day is always challenging, but I'll try to keep you guys entertained and make sure that things aren't too boring and too much for the end of the day here. So my topic today is titled "The Internet is Fine. I'm on Facebook right now." And this is basically a discussion about research networking and why it is different from the normal enterprise networks that universities and businesses tend to run, and just some of the differences and ways that these have changed. All right. Guess I have click control there. All right. So we have a lot of differences today. So the internet as it is today and networks as they are today tend to support a lot of things in our lives. It's pretty ubiquitous. We always have internet connections in our lives, whether we're on our cell phones or laptops or wandering around, that sort of thing. And it tends to work fairly well. Most people have good experiences on the internet and are able to do what they need to do, even over less than stellar connections. Most of the things that people tend to do tend to work fairly well. You can usually get your cat videos when you want to. So in talking about that, let's talk about who I am real quick. So my name is Wallace Chase. So I'm the head of IT infrastructure for the University of Otago in New Zealand. I've worked for a bunch of other places though, as you can see from the logos down at the bottom of the screen there. I started my career as a network engineer many years ago and moved up into where I'm now running IT infrastructure, which includes support of a national supercomputing center and networking and telecom and a bunch of data centers and that sort of thing over here in beautiful New Zealand. All right, so let's talk about some networking. And what I'm going to do real quick with you guys first is I'm going to take you through basically a crash course in networking. So if anybody out there has quite a bit of knowledge around networking or is a network engineer, you can basically just tune out for the next 15 minutes or so, because you should know all this stuff already, or you can simply chime in and correct me when I'm wrong, because at this point it's been several years since I've actually done real networking work now that I'm more of a talker than an actual doer. All right, so will this make you guys a network engineer in the next couple minutes? Well, no, it will not make you a network engineer over the next couple minutes, but it will at least allow you to interpret what the networking community is going through and what they're doing in support of research and how it all works. And of course, fighting the fire of the day is something that every network engineer is very familiar with. All right, so starting out with a little networking 101 here, and this is to take you basically through the OSI diagram. So most people should be fairly familiar with this if you've studied anything at all within networking, but it goes from the physical layer up to the application layer. And this is basically just a way that networking professionals use to be able to describe the networking stack and how data moves from point A to point B across networks. So of course, we start with the physical layer, which is cables and stuff like that, and all the way up to applications where you've got actual end user things such as PowerPoint, which we're using today. All right, so starting with a fairly simple network diagram here, you can see that we've got the internet as a mystery cloud there at the top, simple firewall, some clients connecting via wireless, and some clients connecting via a switch, all through a router. With a simple file server there in the middle. So we're going to be concentrating mainly on the first three layers here for this part of the discussion. All right, so first we'll talk about the physical layer. And the physical layer is basically the transmission and streaming of raw bit streams over physical medium. So this is your fiber, this is your copper connections, or your radio frequency space if you're dealing with Wi-Fi. Next up, you've got the data link layer. This is basically, if you hear a network engineer talk, they'll talk about layer 2. And this is layer 2. This is where you've got everything on one network together. Things can talk to each other on that network, but can't necessarily transit out of that particular network to another network. Okay, within layer 2, you have frames, and these frames contain physical MAC addresses. Physical MAC addresses are basically the individual IDs of pieces of equipment on the network. Okay, so you can look at this and kind of see what a frame looks like on the network. So you'll have that in red there. You'll have the destination MAC and the source MAC address. These are unique identifiers for pieces of gear that are connected to a network. You then, in the light blue there, have the IP addresses. You guys should all be fairly familiar with IP addresses and what they represent. What I like to do is kind of relate this all back to the post office, because people tend to understand that very well. MAC addresses are like your name. So if you send a letter to a building and it's addressed to Wallace Chase, it'll go to the mailroom in the building, and then they know where Wallace Chase is, so they'll send it directly there. Whereas IP addresses are like the actual address of the building. So the US Postal Service, for instance, would know that the building I'm at is in such and such a city, on such and such a street, such and such a location. And then we have layer 3, and that's where things start to get very interesting, and that's basically where you can interconnect networks. So it doesn't do you a whole lot of good in the modern day and age to have those two PCs or those two phones just talking to each other. Within that network, within that switch, you want to be able to talk out to the rest of the world. You want to be able to consume content off the internet. You want to be able to publish content, and that's where layer 3 comes in. Again, layer 3 is kind of that blue area there of the IP addresses, and those act as basically addresses for the network, no different than the post office or the address in your house. So there's a bunch of different ways that you can take networks and interconnect them or build them out in the world today. All sorts of different topographies that you can use, and usually you'll almost always have a combination of these. So you'll often find mesh or fully meshed within data centers. You'll find trees sometimes out in networks, and you'll find partial versions of all of this out there. And of course, any network diagram that you look at is very much simplified as to what's actually going on under the hood. So this is, for instance, a network diagram from the Supercomputing Conference network back in 2018. This is a very simplified version of actually what's going on under the hood when you think of the things that I just talked about with the different networks and the different layers and that kind of connecting everything together. So in networking, you have a thing called a three-way handshake that basically one device, if it wants to talk to another device, will send out what's called a SYN packet. That will get sent back along with an acknowledgement from the other device, which will then acknowledge again, and that's what we call the three-way handshake. And then at that point, those two devices know about each other, they know they can communicate to each other, and they can start sending information to each other. So when we talk about TCP/IP, which is something that a lot of people would have heard about, that's basically the Internet Protocol, the address system of the Internet that I was talking about earlier there. And it's made up of 4 octets if you have an IPv4 address. I won't be talking about IPv6 too much, but just think of that as bigger, more dense addresses than the IPv4 addresses that most people are using in this case. So those different octets represent different things. And that's all controlled via the subnet mask on there, which we'll talk about a little bit later. But you can see in that example there in kind of the gold yellow there how you can go from a part of the address represents the very large company, and then a smaller company within that space, and then a smaller area, basically an individual network, and then the actual end up host name. So with an IP address, you can tell a lot. If you go through and you look at it, you can tell exactly where this is located and who it's connected to. And that's how the various networking systems are able to actually direct traffic around the internet. So TCP/IP, you can think of it kind of as a puzzle. So what it does is it takes a large data set or a large piece of information, and it'll break it down into individual letters, basically, to be sent through the internet. It'll break it up and then it'll travel there. It doesn't really matter all that much if those individual letters take different paths or different things happen to them en route. They'll all get to their destination, hopefully, and then be reassembled on the other side. And that's what TCP does on the other side. It'll reassemble that puzzle and put it back together. It'll also check to make sure that all the parts are there, that they've been received in the right order, that sort of thing, put it all back together, and then say, okay, I got the whole thing. You can move on and do something else. So how did we get to this being the way we do networking out in the world? Well, so everything started out, and actually this picture here is actually I believe it's a recreation, but of the napkin that was drawn on at Xerox PARC to actually for the first idea of what a connected network would look like, and calling it the ether. So you can see radio ether, telephone ether, all those sorts of things, and that's where we get Ethernet from. So ARPANET was kind of the original iteration of the internet way back in the day, funded by the Department of Defense in the US, and primarily built as a research project in order to support the launching of nuclear missiles. The goal was to have a command and control structure that was robust and was decentralized and could self-heal, and could maintain communications even if large portions of it were disabled or taken out. So with that in mind, you think that the internet was built originally and designed originally to be survivable, resilient, decentralized, and very fault tolerant. And those are all very good things. However, there are some things that come along with that. For the internet, it works very well. If you're decentralized, that means that it can grow and evolve quite well. Everybody can have their own part of it, and it doesn't rely on one central agency or one central business to be able to support that or build it out. Fault tolerant, it fixes itself very easily. If parts of it go away, it can reroute and rearrange itself, and traffic can still get through. If you think for a minute about when you talk about fault tolerance, and you think about your cell phone real quick and how you're able to stream videos while walking down the street, and how complex that actually is behind the scenes for the network involved, where it's changing between cell phone towers, maybe changing between Wi-Fi and the cellular signal, that sort of thing. And being able to do all of that while you just casually walk down the street is pretty incredible, actually. Delay is not a problem for most of the internet. So most of what you're doing, if you click on a page and it takes an extra second or something to load, no big deal. There may be a whole bunch of things happening in the background while things are rerouting and changing around to try to get your traffic through. But for the most part, that's not a big deal for what most people do on the internet. Precision is not required. So if there is a small error in the transmission, something like that, that's not a big deal. So most streaming video things such as this, where on Zoom, where we're streaming right now, actually don't do correction. If they miss a packet or if they miss part of the transmission, they won't bother to retransmit it, because it doesn't do you any good to get video signals or audio signals out of sequence. They just ignore it and go on. You may get a little bit of a stutter, you may get a little bit of a robot voice, but it just goes on and continues to work. The internet is also largely consumption as opposed to publishing. So you're largely consuming content, bringing it down to you, basically viewing it. You're not doing a whole lot of publishing, although there is a decent amount of publishing that happens. That's becoming more and more down nowadays, but it is still very heavy on the consumption side of things. And this leads to things called CDNs, which are content delivery networks. So when you, for instance, if you're in New Zealand, like I am, and you're going to go to Netflix and you're going to watch a movie, you might think, well, Netflix is headquartered in California. They have data centers there. I'm streaming that movie all the way from California, but you're not. Netflix and other companies like that, pretty much all large companies, Google, Facebook, Twitter, all these companies host what's called CDNs, or are part of communal CDNs, where they publish their most used content, or in some cases, all of their content, out towards the edge on individual service provider networks. So this works really well. Bandwidth across the ocean, for instance, is a little more constrained than it is sometimes within a country. So it works really well to have those nodes there. It works well for your service provider to host those CDNs, because then they don't have to pay to transit that network outside of their network. They can just service it right from there. And it works pretty well for you as a consumer, because you're getting your content pretty fast, because it's not actually coming from across the world. It's potentially coming from a server room within your city even, where you're actually getting most of your content from. And quite frankly, most people on the internet are watching and consuming pretty much the same content. It's not quite as varied as you would think. Think about what you do during the day. Normally, when you're just scrolling around on the internet or something like that, looking at your Twitter feed or watching, consuming Facebook or YouTube videos or something like that, you're doing the same thing that a lot of other people are doing. So you can push a lot of that content out to the edge and host it very close to the end users. And that all leads to good profitability for these companies. Okay. Now, why this doesn't work very well when it comes to research data is the exact same list there. So while with the internet, you think lots of little things, when you think of research, think of fewer large things and how much more specialized that is. So the decentralized nature of the internet, it's not totally a thing that doesn't work well, but it does make things much more difficult in the fact that when you've got something very large, and you think of that truck there trying to haul that large whatever it is down the road, if you have to coordinate through multiple towns and multiple police departments and multiple Department of Roads and stuff like that, it gets more difficult the more you have to coordinate with to get that wide load through. If you're only coordinating with one entity, it can be a little bit easier. When we said before, we said that it's very fault tolerant. Well, research data is not necessarily as fault tolerant. So you don't want faults to happen. You don't want to lose data. You don't want to miss parts of data. You want it to come through as it was originally done, because that's very important when you're talking about genome sequences or something like that, to have the data come through exactly as it was originally put out. So delay is a problem in that case, and delay becomes more of a problem the larger the files are that you're trying to move. So the bigger the data you're trying to move over, the longer the distance, the more delay becomes a problem. And we'll talk about that more in detail here in a little bit. Again, precision is required. Consume versus publish. We're all of a sudden into much more of a 50-50 split there, instead of just being consumers of data. We may have researchers who do just consume data, and we may have researchers who do a ton of publishing of data. We'll have research centers, research instruments, those types of things that put a lot of data out there onto the internet or out there for people to consume. So all of a sudden, your network that you're running as a network engineer on a university campus becomes much more of a content provider than a content consumer. CDNs basically don't exist when it comes to this. A lot of what we're delivering when it comes to research data is unique. It's not stuff that is massively, the same thing isn't used by a lot of people. There's some exceptions to that, where there's genomic repositories and stuff like that for data that is fairly commonly used. But for the most part, it's very unique data every time that it is moved around. And I hate to break it to you, for anybody who wanted to go into this business to make money, there's no profit in research networking. Okay, so let's talk about the big three here real quick. And the big three for research networking is packet loss, latency, or round trip time, and buffer and window size. So if you guys want to do an interesting little experiment right now, you can actually click in your Zoom client and go to your settings and look at the statistics, and you can actually see there for the session that you're running right now. Whoops, sorry about that. You can see for the session that you're running right now what the actual those big three are for the packet loss, jitter, and latency for your individual connection. Can't see your buffer or your window size, but that's not important for that. So let's talk about these individually here real quick. So if we remember back to what I said earlier, this is a slide that you've already seen, how TCP/IP is basically sending those individual chunks of data and then reassembling the puzzle on the other side. Okay. So when TCP encounters packet loss, so if along the way something happens and you lose some of those packets, either it just didn't get from point A to point B, think of this as lost mail. The mail truck crashes en route, the envelope goes off the side of the conveyor belt and flies down into a corner, gets stuck out in a rainstorm and the address is washed away, whatever happens. In the networking world, that could be a dirty fiber connector. It could be a network card that's introducing errors and dropping packets. It could be congestion where the instrument just simply couldn't handle it and is dropping it, that sort of thing. Well, TCP, again, was built to be very resilient. So what it does is it automatically backs off on its sending rate. So it says, oh, you obviously you're losing things, so you can't handle things that fast. So I will basically back off on that. It reduces the sender's notion of the window. So it closes the window down, makes it smaller, and says, okay, we're going to send less data. Now it hopes that that's just transitory and that everything will be hunky-dory in a minute. So it ramps back up again to attempt to get the maximum speed out of the link. However, when it keeps doing that, things go bad. Now, over the longer the latency, the further you have to send something, the longer that control loop is for that ramp up and ramp down. The longer the distance, the longer the latency, the harder and harder it becomes for TCP to do anything other than to actually recover from loss. So it ends up getting stuck where it just ends up getting slower and slower and slower until it finally gets to a state where it can actually send that information, even if there's actually more bandwidth than that available across that. Okay. Now buffer and window size, so one of the big three, as I said there, and these are all very interconnected. So that's why I put them in this order here. So they determine the amount of data that the kernel will keep in buffers for the connection. And the window is what's advertised over the TCP connection. So the larger the window, the more data can be in flight at any one point in time between the two hosts. So things are happening very quickly here, and you don't want to necessarily completely wait every time. This is how big of a chunk of data you can send before you need to get an acknowledgement that the other end actually got that data. Okay. So large windows are absolutely required when the latency is large. So you want to the more latency that you have, the more time it takes to get from point A to point B, the more you want to be sending before you get that acknowledgement. Think of it this way: if you're sending a shipment across the U.S. from New York to Los Angeles, and you put it on a truck, if you wait for that truck to get all the way to L.A., place a phone call and said, "Yep, I got it here," before you send the next truck, it's going to be a while. So you want to have multiple trucks all driving at the same time to do that. And that's kind of what this is happening about. Now, the network cards themselves, they don't recognize or care about TCP. Remember, they're at that physical layer of the network. They're a physical device. They just know simply, hey, I'm a 10 gig network card. I can toss out packets at 10 gigs. So I will toss out packets at 10 gigs. So that's where that window size comes in very important. Okay. So if there are any buffering or queuing problems along the path, those packets will be dropped, TCP will back off, and you get into kind of this loop of constantly degrading performance. And this is especially key over long latency or long distances. And the round trip time is fairly self-explanatory. This is the time it takes for that truck to get from one end of the country to the other. Okay. So as I was saying kind of before there and explaining as we go, TCP windows are much smaller for low latency connections. So if you're very close, you don't need those larger windows. So it's not as bad if things don't get there or get retransmitted, that sort of thing. It's faster to recover. You find out about the problem before it's destroyed a whole bunch of the data or lost a bunch of the data, and you can retransmit. But when you're doing this over very long distances, if you lose one of those big windows of information, then it's a big deal to retransmit that. And things will start to come in out of sequence and stuff like that and really affect it. So the longer the latency, the more impact that this has. And you can see this. So ESNet, which is a wonderful resource, and I'll be giving you guys if you guys haven't checked out ESNet's website, I'll have a link to it at the end here. It's absolutely wonderful for information on this. They did this many years ago and showed this is the network card that was misbehaving in one of their routers. And it was 0.0046% packet loss, a tiny amount of packet loss that's actually happening there. And you can see in the purple line there, that's if there is no loss, that's the kind of throughput that they would get. But with that 0.0046% loss, you can see as soon as you go outside of the local network, the network within a building or within a campus even, and go onto that metro or regional network, the performance just craters immediately. And you're all of a sudden into this pretty terrible performance. And that's even with some different protocols there that handle things a little bit better, supposedly, than TCP, just pure TCP. So another thing in networking to think about is MTU and jumbo frames. So this is the amount of payload an individual frame has on it. So anybody who's done supercomputing and who supports supercomputers will know all about jumbo frames, especially in your interconnects and that, where you want to be able to have the maximum amount of data possible in that frame. So think of it this way: you've got all this overhead of the preamble and the destination MAC and all that sort of stuff in there. You want to be able to put as much then data on that as possible, and you can do that assuming that your link is fairly clean. Now, the interesting thing about jumbo frames is that they're not enabled by default. The standard is 1500 bytes for a payload on a frame. You can go up to 9,000, but the standard is 1500. And it's very difficult to tell if everyone has enabled that ability for jumbo frames across the link, especially if you're going long distances. So this is something that gets people. This is the bane of a lot of network engineers' existence, because you have one device in the link that is still set at the default of 1500, and all of a sudden none of that. Doesn't matter that you have everything else. It doesn't matter that you have the other 37 devices all set to support 9,000. That one device basically will block everything up and things just won't work at all. Okay, so let's talk about using protection here for a second. And don't worry, I'm not talking about either guns or contraception here at this point. I want to talk about security instead, network security, information security. So in talking about how normal things on an enterprise network don't work very well for research data, we'll kind of go through this list here. So what is a DDoS? So think to yourself for a second, what is a denial of service attack, and what does that look like? Well, it looks like somebody sending a large amount of data aimed at you or a device or a server or something like that, to overwhelm it, to flood it, to knock it off so that nobody else can access it. Well, research data flows are large amounts of data sent in a particular direction, hopefully at a device that doesn't get overwhelmed and is able to handle it. But to the network operators along the route, a DDoS attack and a very large research data flow look exactly the same. So you end up with something that, to their tools, especially if they have automated tools, and most ISPs now have automated DDoS protection that kicks in as soon as they see something that looks like this. They'll kick in and they'll shut it off. So your research data will look like that. So that's where normal internet ISPs start to have some real problems when it comes to supporting these large data flows. You'll have them come and talk to you and say, oh, yeah, hey, we got 10 gig connection, we got 100 gig connection, whatever. And then the first time you try to use it, bam, you trigger all of their DDoS protection, and your stuff gets locked out immediately. Intrusion prevention, again, very similar thing. These large research flows don't look normal to a baseline-based system like an intrusion prevention system that's just looking at what's normal for the network, and anything that's abnormal gets immediately shut down or clamped off or black hole. Firewalls. Firewalls are a tricky one. So firewalls, often you can buy firewalls that have massive amounts of throughput with them. But oftentimes that massive amount of throughput, and think again, who they're selling firewalls to. They're not selling it necessarily to folks that are doing big data transfers very often. They're selling it to people who are running normal internet networks. So they may say, oh yeah, we got 10 gigs of throughput. Well, you have 10 gigs of throughput for 10 gigs of a lot of little stuff, but you don't necessarily have 10 gigs of throughput for one large stream coming from one source or one destination, or even broken up into multiples, that it can actually handle. So a lot of firewalls, and some have gotten better recently, but they're very expensive, the ones that are. Most of them will break up streams. They won't handle a stream any larger than 1 gig. So the way they deal with the processing of stuff, they just can't handle more than 1 gig. Firewalls are always a problem there. Many firewalls too, once you get up to those kind of numbers, the actual forwarding ability of the boxes can be a little bit sketchy from what the actual advertisement would say. Let's put it that way. Access control is another one. Can you actually get the data from point A to point B? Can you authenticate? Can you get through all those sorts of things? And the ability to audit this. So the information security teams are going to want to audit. They're going to want to know what's going on. They have requirements that they have to meet for this sort of stuff. And is your research data able to meet those requirements to satisfy what they need to do for their job? So this all comes down to, and I like to describe it this way: if people have heard of the Pareto principle, and I kind of modify it a little bit here, and I like to use this example here. So this is the Consumer Financial Protection Bureau, and this is their list of consumer complaints, the top 100 consumer complaints. And this is a good example here of, basically that 95%. So if you're the Consumer Protection Bureau and you want to deal with consumer complaints, and you take a look at that, which end of this graph are you going to deal with first? Are you going to deal with the things that maybe only have a couple hundred people complaining about them, or the thing over to the left that has 30,000 people have complained about it? The most bang for your buck is to go for the left side of the screen and work your way right. There becomes a diminishing return to actually dealing with any of those further over. You wait till they become bigger problems, and then you deal with them. So another way to put this is, if you're an ISP, if you're an internet service provider and you're providing networking for the masses, if you put in 20% of the effort and you get 80% result, hey, profit. That's how you make money right there. If you put in 80% effort and you only get 20% of the people satisfied, you're not making money, probably. And the goal of internet service providers is to make Scrooge McDuck amounts of money. They're not in it as a nonprofit or to just help you out because they're good people. They're in it to make money for their shareholders, and to do that, they need to satisfy the needs of the most amount of people who are going to pay for their service. So again, commodity networks, so those normal internet networks, and even normal networks on a university or college campus, they're great for normal traffic. They're designed for that. They work very well for that. They're very resilient. They can move a lot of small things around. They're absolutely great and they've been tweaked and modified and are extremely efficient to deal with content that comes off of CDNs, and they're available almost everywhere. You pick up a Starlink terminal and you can get internet on the top of a mountain on the east coast of New Zealand in your camper van. Ask me how I know. They're not so good. They're not at all optimized for large flows. They just don't deal with that much. That is not their core business. The tiny percentage of people who want to do that, it doesn't make sense for them to re-engineer their whole network to support them. It can be very expensive to do it. So even if they will do it, it can be very expensive to have them do it because they're basically re-engineering a whole thing for you. They often have very suboptimal routing and peering for point-to-point research traffic. So you think about how we're moving data around doesn't necessarily match with how the rest of the internet is moving data around. It can be very suboptimal. A lot of these companies as well will often buy connectivity. So a company like AT&T, as big as they are, don't necessarily have connections to every place in the world. They sell transit. Basically, they buy and sell transit. They buy the ability to transit their traffic over other people's networks in order to get it to where it needs to go. But they're doing that often at the lowest bidder, not at the one that's going to necessarily make the most sense. So you may have traffic taking very, very weird roundabout routes, which again isn't a big deal if you're just using the internet as a normal person. But if you're moving a large amount of data, it's a very big deal. Throttling, queuing, traffic shaping, just destroy throughput. Those are all things that make it so that they can oversubscribe their networks and sell much more capacity on a network and that sort of stuff. And I like to say they don't care because, again, they're making money off of this. Commodity networks designed for lots of small stuff. High speeds aren't always available. That's not necessarily as true anymore. You can get 100 gig circuits if you want to pay for them. It's a lot of money. The big one, though, at the bottom there is if you have issues, good luck getting any help. So a round of people on here, use the thumbs up thing in the reactions. How many people have called your ISP because you've had a problem with your internet and gotten absolutely wonderful, great service immediately? All right, so nobody. Good. Can tell I'm speaking to a mainly US audience because pretty terrible service providers in the US. So how many people have called into their internet service provider and gotten terrible service? Here's where we see if people are just all asleep or if people are actually there to react. All right, good. I've got at least 2 people that are still awake, so that's wonderful. All right, I see some people in the chat as well. So what is service on an ISP? So service is if you call up and you call up Comcast and you want to get internet connection to your home. So that service is an internet connection to your home. Ah, that was just sarcasm. Okay. Now that's good. Yeah. What is service? All right. So the way I like to put it, though, is it's not necessarily those companies' fault. Take the sloth and the giraffe. Each of them are very efficient leaf-consuming machines. But if you try to merge them together, you can get an abomination. So don't even try to do that. There are other ways to do this. So the solution is a network built and designed and operated by and for the research community, which is what we're here to talk about today. Long roundabout way of getting you to where we're actually talking about what we're talking about today. So let's think about networks of networks connecting to networks of networks. So let's talk about this. So there is a large community out there of networking providers that exists solely to support the research networking space. And we'll kind of start on the macro scale and work ourselves into the campus to the micro scale here. So we first have international networks. So there are international networks all over the world. Some of those are for entire continents. Some of those are for individual regions within continents. And some of those are dealing with continents that are also countries. So for instance, ARANET in Australia, they could be considered an international network because they're a little bit of both. So is RIANS here in New Zealand. It's a little bit of both. But you have these networks that make connections all across the globe, that handle subsea cable links, all those sorts of things. So here's from just taking from the RIANS site here in New Zealand. This is a very, very simplified diagram of what all those connections look like around the world that are specifically set aside for research traffic. So for research internet traffic. So you can see there's a very large network across the world that's all interconnected. Different countries, different organizations all fund it, mostly not for profit. In the US, a lot of it's funded by the National Science Foundation, for instance. In New Zealand, a lot of it's funded by the Ministry for Business and Innovation. So there's a lot of different ways that it's funded, but mostly through governments in order to support this research networking. It's a very large worldwide collaboration of networks that does this, that hits pretty much every part of the globe. So taking New Zealand for an example, because I'm rather partial there, our connectivity that connects us to the rest of the globe goes up through Hawaii and over into Oregon in the US on the Hawaii cable system. And then also over to Sydney in Australia. There's some work going on right now with a cable system that's coming from, that's a potential from Chile directly over to New Zealand, and another one from Melbourne over to New Zealand as well. But you can see there's a lot of different cable links, and those connect up different parts of the world. So our particular connections in New Zealand, as I said, we have connecting to Pacific Wave in Seattle with University of Hawaii in Hawaii, ARNet in Sydney, Gorix peering in Guam through the University of Guam, and then we have a bunch of direct peerings with other NRENs. Okay, so this is all done primarily with undersea subsea fiber systems, which are pretty interesting. So I've got an entire talk on subsea cable systems. As I came to New Zealand, this became a very big interest of mine because we're so reliant on these. And it's an absolutely fascinating world to be involved in, or to learn about exactly how these things work, and actually how small subsea cables actually are. And how, for the most part, they just sit on the ocean floor across thousands of miles. There's a particularly interesting picture of a cable getting loaded into a cable ship. It'll often take them nearly as long to load the cable into the ship as it will to actually go out and deploy the cable, because you absolutely cannot have a tangle. So there's also around the world, there's several places where major international networks tend to all come together. I'm not going to highlight all of them, but the one I'll highlight is the Gorix exchange in Guam. So that is where a lot of the Pacific, specifically the Western Pacific, comes together, and has different networks from Japan and China, Hong Kong, New Zealand, Australia, all come together and join there, and are able to utilize each other's connectivity. So very much unlike commercial networks who have to buy from each other in that, we tend to work in the research networking community on open exchanges where we're able to connect into each other and be able to pass each other's traffic to each other. So then we have national networks, and national networks is just what it says. It's a network that exists within a country to service the needs of that country. So in the US, you guys have Internet 2, which does a fantastic job. But you also have a couple other networks within the US as well. You have ESNet and a couple others. In New Zealand, RIANS, although it's international network, it's also a national network feeding the country. So a good example is Internet 2's network that connects across the entire country. And they have a backbone that consists of very high-speed links that do that. And then off of each one of those high-speed links, you'll have individual connectors that'll connect off of those, that'll then feed out, branch off into individual areas of the country, which we'll talk about here in a little bit. ESNet also has a very large network that also spans the globe, mostly to get over to CERN, the super collider over in Europe. So same thing with RIANS, and here in New Zealand, we have a network that spans the entire country from the North Island through the South Island. And then you have other, basically I could go through this all day long showing different pictures of different networks in different countries, but this just gives a little bit of an idea of the scale of this and how much money and effort and thought has been put into how we connect up all our different research institutions, our universities, our different research centers, that sort of thing, how we connect them and provide this high-speed connectivity. So then we've got state and regional networks. So we've got in the US is a very large place. Each individual state, or in some cases an area, a coalition of a couple states, will have a network that services that particular area. In different parts of the country, you'll have these different agencies that'll then have connections off into the individual universities there. And then in some areas, like in New Zealand, we have one network that's both the national, international, and the regional, because we don't really have individual states. Here's an example of one that I'm fairly familiar with from a couple of years ago within South Carolina. So you have where it comes in, connects into Internet 2, it connects into the Southern Crossroads in Atlanta, which is a major connector site in the Southeast there. And then it goes out to the different research universities and colleges within the state. So talking a little bit about those exchanges and those POPs, there, as I said, there are different areas around the country and around the world, for that matter, that have a large amount of connectivity that all comes together at that one point. And those are particularly interesting to know about. As I was talking about with the Southern Crossroads Exchange in Atlanta, they're very active in supporting research networking and supporting the different universities and that connect into there. And sometimes you have universities that connect directly into one of these exchanges instead of connecting into their state's network just because it happens to be very convenient for them to do so. And then you have your local networks. So then you have all the individual institutions that are connected into your into the research network. So you can kind of insert your logo here of your institution. If you're in a major or even a mid-sized research institution, you're probably connected into a research network. So then you've got your network within your individual own, I guess you could say, place that you're at, within your university, within your research institute, that sort of thing. And these can be very complex beasts. So you've got a lot of things going on here, and it becomes almost more complex the smaller you get when it comes to these networks. Why is that? So local area network, you're spoiled for choice. It's like the pick a brick wall at the Lego store. So LAN networks are like Legos. You can put them together pretty much any way you want. There's no really wrong way, although I have seen a couple networks that have definitely been built what I would consider to be the wrong way. But there's a lot of different ways that things get built and put together. And so it can be a very complex environment within an individual university. You have a minefield of equipment within a university or a local area network. Often you have various ages of gear, you have various things that's been built over the years. It's often a very iterative process or a very organic process, I will say a lot of networks grow in. So you have a lot of different equipment, a lot of different things, a lot of different, and I say random, but I'd say different security requirements. Because you have to remember that a university network is a very unique place to do networking in. If you work in a bank or if you work in a hotel or something like that, you're pretty much providing one form of networking. You're providing connectivity to the guests in the rooms, maybe a little bit of connectivity to the front desk, that sort of thing in a hotel environment. If you're in a bank, you're basically providing a highly secure network for that bank. Within a university, you're basically doing every type of networking. You have every environment that is out there all on your network, all together, coexisting, being supported by the same group of people for the most part. So they're very interesting. Universities are very interesting places to work at when you're doing networking, and they're very complex places because of that. You can have students in the dorm, researchers in a research lab, a bank in your student union, next to a food service place, next to the administration of the university, that sort of thing. You have lots of different, basically any type of network you can think of is there. So what's the deal with DMZs? So you might have heard this term before, science DMZ or DMZs. And it's not this type of DMZ, but that's a good way to say it. So I'm going to give a little bit of an example here as to what actually a DMZ is and why you need it on your network. So let's talk a little bit about what makes up a university network. So you've got those students out there. You've got what I call business IoT, which is all the stuff that connects to the network that makes the university work. Card access control systems, CCTV, HVAC controllers. There are thousands and thousands of things now connecting to the university network, from vending machines to cupcake delivery robots and stuff like that. You never know what's connecting to your network in a university. So there's a lot of that kind of stuff out there. You then, of course, have the research and teaching, who are the primary purpose of the institution, of course, and are often sometimes starved for resources there. And then you have the enterprise systems. So you have payroll, you have student records, you have all these types of things. Those are kind of those big systems that IT departments tend to spend a lot of time and energy on. The business of the university. Now, of course, all these have to be secured. All these have to be locked down. They have to have security in some way, shape, or form. And of course, the problem with that is, I mean, you've got the students are breaking out just as much as they're breaking in. They're as much of a threat as they are a threat from others. So let's talk about the university enterprise network here for a minute. And I'm going to use a bit of a hard for me to explain. So I'm just going to explain it this way. So we're going to explain it using this picture here. All right, so we've got the university enterprise network here. Let's just call this the internet connection for the university. We'll call that the firewall, so that security layer that's around the university network. And yeah, of course, you have the IT security team up there standing watch, making sure that everything's going okay and that nobody's getting in who shouldn't be. And then, of course, you've got the help desk / bureaucracy / paperwork / the reason that we all love working for universities so much, which is the absolute efficiency of the places. Okay, so I should have warned you a little bit earlier. I'm going to be using a lot of analogies here for this particular section. All right, so my first one here is computational research equals a velociraptor. So and hold on, stay with me here for a minute, because I'm going to hopefully convince you that that is correct. So in order to give you some irrefutable proof, I'm going to use a Venn diagram, because that's a good way to do this, I figure. So computational research and a velociraptor, they both need to be very agile in what they're doing. And you move very rapidly. The environment changes a lot there. It's more effective in groups. So if you collaboration going on, it's much more effective if people are able to collaborate and work together. And it tends to consume all available resources that it can get a hold of. I think they're both actually pretty cool too. So that's another thing that's same on them. There are a couple things that are different about them, and that one's a reptile and one's not a reptile, but we'll just ignore that for now. All right, back to our prison analogy here. All right, so the computational researcher comes along. This part requires some reading. I'm not going to read everything for you. Bureaucracy asks what's going on. I have some important research data. Highly important to them, to the educational community and mankind as a whole. How many researchers have you had that are able to very effectively give that spiel, how important this is? Needs to be reasonably secured, available to research peers. The data sets are kind of big. Don't know how big they are, but they're kind of big, and they may need to be shared. So can I get a spot for those? Can I have some infrastructure that'll work for that? Of course, the guy at the help desk has no idea. I get to see my wonderful animation skills coming in here. Oh, look at that. I should have been a film director. Okay, so just a silly way of seeing if you guys are awake and see if anybody all of a sudden wakes up in the awkward silence there. But computational science tends to take over as much capacity as it can within any system. So if you put a researcher onto your normal, VMware cluster or something like that that's run for the enterprise, and you try to have them use it as a supercomputer, they're just going to want more and more resource. It's just going to take away. It's going to potentially destabilize the environment for those business systems, that sort of thing. It's the same way with networking. So you let a computational researcher just loose on the network, they're going to immediately oversubscribe the bandwidth in their building, in their office, in their room, whatever. Firewalls are going to get in the way, get overloaded. Things just aren't going to work very well for for anybody, not just for them. They'll be frustrated, but also everyone around them that's connected to the same network may be frustrated as things get overloaded and overwhelmed and shut down. So, I mean, you can obviously go to you can go to the people that run those enterprise systems and ask them for more resources. But of course, you know, when it comes to running payroll or running somebody's simulation in MATLAB or something like that, well, you know, you're gonna get that answer. Sometimes you'll get the answer of, hey, how much money do you have? We can make this work, but we need a lot of money to do it. So this results in a lot of adverse consequences. So network performances for everybody, and it ends up with probably not necessarily an actual physical hard drive anymore, but an SSD in a box getting sent from one place to another in order to transfer data, which is, of course, a security person's worst nightmare, but is often what ends up happening. Okay, and of course, being able to collaborate and move data around is extraordinarily important for modern day research. The days of a researcher holed up in a lab all by themselves making giant discoveries, although I'm sure it does still happen, is a bit behind us now. And now things are collaborative between institutions, between countries, between research teams, that sort of thing. And often when you're dealing with these large amounts of data, that's exactly what's happening, where multiple people are analyzing it, multiple people are working on it. And that's where another specialty network comes in, which is that science DMZ. So that is that ability basically to be able to have a section of the network that is separated out from the main university network. So you kind of leave that part alone. You let it run like it does with its security and all of its things and the students mucking around and breaking things. You leave that over there. And then you build basically a separate portion of the network that has high-speed dedicated links where we can take care of things like jitter and latency and round trip times. We can take care of things like the MTU size in all the equipment, those sorts of things, and make sure that there is a nice fast connection there for the researcher that works for them, and make sure that they don't break all the rest of the network in the process. And that's basically, at the end of the day, what a science DMZ is for. It also allows the security team to feel a little bit better in the fact that this kind of specialty stuff is all happening over here, segmented off, and can have specialty security controls around it, and that they're not having to buy these big boxes that have to handle these massive amounts of flows and stuff like that do the entire campus. Now, does everybody need a science DMZ? Well, as with every question, when you ask a network engineer, the question is going to be depends or maybe. And there's a lot of different science DMZ architectures. So this is very much the same as what I said earlier about LAN about LAN network designs. Is they're kind of like Legos. You can put them together any way you want. There's a bunch of different ways to do it. And I've decided just purely myself that there's about 6 different ways that you can do it. And I'll go through those real briefly here right now. So one is the brute force method. You basically build another network out to the end user. You build it on demand, and basically if you have a researcher out in an individual building or something like that, you build out a network to them that can support that science DMZ. It's a physically separated thing. Long lead times on that, sustainability of it. You know, how do you sustain it, especially if then that researcher 6 months later goes and moves to another building, and it's pretty expensive to do. The other method that I like to call is the apply money method, where you basically build a science DMZ that stretches pretty much everywhere within the university. I know a bunch of places that have done that, and in some places it makes sense, especially if you have high concentrations of data intensive researchers, but it does have sustainability issues, and you can have some problems with it, getting broken and stuff like that due to the way researchers use it. Then we've got the help me help you method, which is where we can basically just replace key components within the network. And this is often the first place that universities or institutions go when they're building a science DMZ. They'll replace key components, make it so they can build that DMZ out, and then they have the ability to do it at least. Now, it may not go all the way out to the edge where the researchers are, but they've at least got a component of it, and it's starting to work its way into the network. And then there's all sorts of very fancy ways to do it. These are ones that network engineers tend to love to do, which is to make logical separations of science DMZ, virtualized environments for it, all those sorts of things. It can be pretty complex to manage, and you just have to be very sure that you've got the ability to manage that if you do decide to do that and go forward with it. And then there's some special snowflake ones where people have set up very unique networks to be able to support this, or unique ways of doing it. And the questions there is it sustainable? How are you going to actually manage it going forward? And then the method that you'll find a lot of people using, and that IT departments tend to like the most, is to the come to me method. So centralization. I will build you a science DMZ that has the ability to connect at 40 or 100 gigs, no problem, but it's going to be in the university data center. It's not going to go out to your lab. It's going to be in the university data center, or it's going to be in specific places, and you have to bring your equipment to there. Now, this requires a lot of trust from the IT department and the research community trusting each other to be able to do that. And IT needs to be able to set it up and run it that way and that sort of thing. But this is very much you're seeing a lot more of this. This does still kind of leave out those instruments. We've got an environment nowadays where a researcher can do genomic sequencing on a little USB drive that'll pump out hundreds of gigs with each run that it runs. You're not going to have them sitting in the data center doing that, so you still have the question of how do you get out to those instruments. But if you've got a on-campus HPC, if you've got centralized storage, those types of things, that really helps, and you get some very big cost efficiencies there. So here's an example of a very simple one that we set up in New Zealand not that long ago with Manaki Fenua Land Care Research, which was basically just a connection into the RIAN's backbone, a science DMZ connection that basically just went around the firewalls and around the core switches, and directly into a dedicated switch for their 3-power SAN that they had. Very simple, very easy, but for what they needed, it worked out perfectly and got around those congestion problems that they were having with the rest of their network. So it doesn't have to be complicated, it doesn't have to be fancy, and you got to start somewhere. So let's talk for a little bit about how we actually then transfer that data. We've talked a lot about the network. I just want to briefly mention, though, about the actual applications that you can use on this. And this is where I will do basically a sales pitch for Globus, because Globus is every network engineer's best friend, in that it's a very good software package that allows you to transfer files, that allows you to set up things. It works very well for centralized data stores. So if you've got a large, like we've got a very large Dell EMC Isilon environment for our high capacity storage, we have Globus nodes set up on the perimeter of that, where researchers can move data in and out of those very quickly. We've got a couple people who still have their own arrays stuffed in their labs and stuff like that. Those are much harder to support. But when you get to this type of situation, it's much easier, and Globus really does make things very, very easy. You can try out Globus. It's completely free to try and move stuff around. Just go to the Globus website and make yourself an account, or if your institution has an account already, your institution may have an account already, so be sure to check on the unified login stuff to see if your institution shows up there, and just go in and try it out. You can go and if you search for ESNet in there, you can find a couple of open data transfer nodes where you can actually download and transfer very large files up to 100 gig as just test files to see how well your connection performs and how well you can actually move data around. So you go on and try it. I would encourage you to. It works pretty well, and it's the network engineer's best friend. Now, I get a lot of people asking me, well, I use SCP. I know how to use SCP. Why can't I just use SCP? And yeah, that's fine and if you're in a very small network with very, very low latency and you're pretty close to your endpoint. But as you can see here with some of these tests that, again, ESNet did a while back, SCP is horrendously slow when it comes to long distance, high throughput transfers. Whereas something like Globus that's using grid FTP on the back end is able to move data at a far higher rate. It's much better about resiliency, that sort of thing. So SCP, great within your own machine or your own cluster maybe, but I wouldn't use it outside of that. Wouldn't recommend it. You can get a lot higher speeds So a bit of a pitch here as well for the ESNet website, and in particular fasterdata.es.net. It's a fabulous resource for all things. You can go in there, you can find out about host tuning, you can find out network tuning, data transfer tools, performance tuning. The team at ESNet has put this together and has run this for many, many years now. It's well curated, it's up to date, and there's a lot of information on there. And if you need help, and for some reason you can't get it from anyone else, you can absolutely email them, and they will help you out or point you in the right direction. So highly recommend. I think it's one of the best resources as far as just raw data about moving data. Okay, so weak links break file transfers. So know your provider, leverage them for help. So get to know your networking team, get to know your local provider. If you're, especially if you're a support person in the HPC world, make sure that you have a contact at your local regional optical network with Internet 2, anything like that. Make sure you know where to go for that help. There are people out there who can help you move data around and help you design things and help you know how to do these types of things and troubleshoot problems. Leverage the online resources that are out there. Networks come in many, many shapes and many sizes, so no two are exactly the same, which is both a blessing and a curse, I will say, in the community. Networks interconnect to make more networks, and networks get exponentially complex the more connections you have. That's what makes this job interesting, and that's what makes, I think, networking one of the most interesting fields to work in, is just the exponential complexity that happens in what seems like a fairly simple thing on the surface once you start to get networks connecting to networks. And if your data has to transit it's your network, and you need to know who to go to for help. So you may need to get help at any stage in that transfer, and especially if you're doing international transfers and that, make sure that you have good contacts that can help you out, and don't be afraid about asking for help. This community, I mean, network engineers aren't necessarily always known as being the most out there and people, but they do absolutely love a good problem. And we love it when you come to us for help, and an interesting problem is always a very good problem to deal with. All right, thank you everybody for your time today. Hopefully we can get those velociraptors riding sharks with RPGs soon, and get that data moved around very, very quickly. I'm available at any time. You can go ahead and email me, ask me any questions in that. If I don't know the answer, I can either lie about it and I'll tell you that I'm lying about it, or I'll send you to somebody who does know the right answer. So, all right. So questions from people here. I haven't been keeping good tabs on the chat here, so I will go ahead and look. Does anybody have any particular questions or anything they want me to go over that I didn't touch on here today? As I scan through this, anybody can unmute and chat if you'd like. Oh, thank you for the saying the slides are amazing. I always wonder if the cartoon nature of my presentations actually goes over well, or if people just think I'm lazy. Seems like a lot of people are having network connectivity problems right now too. How well can I lie about it? Well, I've been in IT administration now for the last 10 years, so probably pretty well. All right. If there's no questions that anybody has, oh, here's a question. What's the difference between a switch and a router? Okay, and that's something I kind of glossed over and meant to talk about, but probably didn't. So a switch is operating primarily at layer 2, although you can get switches that'll operate at both layer 2 and layer 3. And a router is operating at layer 3. So a switch can connect up various endpoints and make them talk to each other locally. But if you want to go outside of that network, basically, if you want your network to connect to another network, then you need a router. And there are, the line between pure routers barely exists anymore. Most devices will do both layer 2 and layer 3. But for instance, a switch that's a normal commodity switch that's out close to your endpoint in your building probably doesn't do layer 3, just because it's expensive. The layer 3 ones are more expensive. So it probably just does layer 2 and then sends all that data up to a layer 3 switch that then can connect networks to networks. Hopefully that helped, Carol, with that question. HPC and SDN. So not quite sure what the question is there. Yes, is the answer. No, so yeah, so SDN, yeah, it's been a lot different, I think, than people imagined it would have been, 10, 15 years ago when it was all the rage and first came out. It's there, it's getting there. I think it has devolved a lot more into individual vendor interpretations of SDN than it has into kind of what the original goal was of a open environment where you could have any operating system running on things. So that's devolved into a lot of different things. If you got a very specific question around that, ask me. What's the difference between internet network and research network? In one sentence. Oh, that's hard. I talk a lot. One sentence is difficult for me. So I would say an internet network is built for the masses, and a research network is built for very specific use cases. I had to say it in one sentence. I could probably reword that into one sentence at least. All right. Well, thank you, everybody. You got my contact information in case anybody's interested, and hope everybody's enjoying the training so far. I absolutely love these. I think this is about the 4th or 5th year now. Sixth year I've come back to these, so they're wonderful. Thank you, Henry, for inviting me back this year.
And thank you, Wallace, for a fantastic presentation. Again, I think we can see through the chat that people are very engaged, very excited, very interested, getting a lot out of it. So a big round of applause for Wallace, albeit virtual. And yeah, thank you, Sagnik. And I have posted his slides already. In fact, we are actually caught up on slides as of this afternoon. So I'm going to stop the recording and then restart it so that we can do our wrap-up session. And let's do that. Hang on.